Well, let's look at the overlap of orbitals between carbon and hydrogen. So carbon has 4 valence electrons, and so this would be its orbital diagram, and we'd see that it has 2 half-filled orbitals. And if this is interacting with hydrogen, each of these could interact with one hydrogen, just like the sulfur did in the previous example. The difference here is that the carbon has this empty orbital instead of a lone pair there. So we're not going to draw the empty orbital. We're just going to draw the s orbital with its pair of electrons, and we have one p orbital here with 1 electron from carbon. It overlaps with the s orbital with 1 electron from hydrogen to form a bond. And there's a second p orbital at 90 degrees to the first one that also, we've got this overlap of 2 half-filled orbitals, and that makes a bond in this theory. And again, we would predict that this bond angle is 90 degrees. Well, this doesn't work as well for carbon and hydrogen, because carbon and hydrogen don't form compounds that are CH2. Carbon will bond with 4 hydrogens at once, not just 2. And when it bonds with 4, we know that the bond angle is 109.5. So looking at it this way worked okay for H2S, but it doesn't work for carbon and hydrogen, and it doesn't work for most other molecules either. So something's missing here, right? An additional concept is needed. The orbitals in a molecule are not necessarily the same as the orbitals in an atom. When these atoms interact with each other, their orbitals can change because of those interactions. This is called hybridization. So that's a mathematical procedure in which you take those standard atomic orbitals and you combine them together to make hybrid orbitals. Those hybrid orbitals are going to look a lot more like the actual distribution of electrons in molecules. They're still going to be localized on atoms, but they're going to have different shapes and different energies than the standard atomic orbitals. Those hybrid orbitals are going to minimize the energy of the molecule by maximizing the overlap. The hybrid orbitals are going to give us better overlap because unlike regular atomic orbitals, which are symmetrical about the nucleus, these tend to be more on one side of the nucleus than on the other, and so you get better overlap. It does require energy to hybridize these orbitals, so it's only going to happen if the result is a lowering in energy. So if you've got an atom, it's not just going to spontaneously hybridize its orbitals. It's only going to hybridize its orbitals if, when it's interacting with another atom, hybridizing it causes the energy to be lowered. So what we're going to look at is just hybridization of the interior atoms, and we're going to assume that the terminal atoms are unhybridized, and it works pretty well. So some general things. The number of standard orbitals from the S, P, D, and F that you get from the atoms, the number of those that are added together is always going to equal the number of hybrid orbitals. So we're not going to gain or lose orbitals. The particular combinations that we have are going to determine the shape and the energies, and the type of hybridization, is it 1s and 1p, or is it s and 3 p's, is the one that yields the lowest energy. So that involves some really icky, in my opinion, calculations, right? So that's beyond Chem 1A. So what we're going to do is we're going to use Vesper theory, electron geometry, to predict the hybridization. We're going to look at the number of electron groups on that central atom and say, okay, that's the number of hybrid orbitals that we need. So let's look at what would happen if we take one s orbital and 3 p orbitals and put them together. It's kind of an average, right? So here is carbon. Its valence electrons are in the second level, and so we have a lone pair in 2s, and we have 2 electrons that are unpaired up in the 2p. If we hybridize these together, now we're going to get 4 orbitals that have the same energy as each other. So those 4 orbitals are degenerate. So this also works with my quantum hotel model. Whoops, that's not S, that's P. And that's, I don't know what that was. This must be an S. So in the quantum hotel model, we thought about these sublevels as being different rooms on the same floor of the hotel. This sublevel has 1 orbital in it, it's got 1 bed. And this sublevel has 3 beds, it has 3 orbitals. And so we draw those boxes together because they're in the same room. So hybridizing the orbitals is like remodeling the floor of the hotel. Instead of having a wall between these 2 rooms, we're going to take the wall out, and now all the beds, all the orbitals are going to be in the same room. They're going to be in the same sublevel. So I took the wall out. The number of beds that were there is the same. We didn't buy or sell or lose or break any beds. The number of beds is the same, the number of orbitals the same. But now what room they're in is maybe a little different. So I used to have an S room with 1 and a P room with 3. So now I have 1 big room, and it has 1 bed from the S room and 3 beds from the original P room. And so we're going to call this SP3 for short. So that's an SP3 orbital. So it used to be in the S room that whoever stayed there paid less money than people staying in the P room. And they paid more money. So now when we remodel this and make it into 1 big room, it's less expensive than the P room was, but it's more expensive than the S room was. So the energy of this is between the P and the S. But they're all the same. It doesn't matter if you sleep in the bed that came from the S room or one that came from the P room. The hotel manager, they don't have cameras in the hotel rooms. They can't tell what bed you're sleeping in. They can only say, okay, well, you're staying in that room because I gave you a key to that room. So they have to charge the same for all the beds. Any questions? Mm-hmm.
Like when you're talking about energy level, so they have to be the same energy level, or they can be different energy levels?
They have to be in the same principal energy level for this to happen.
Okay.
Because on the hotel, the S and the P room are like right next to each other. So yeah, we can just take this wall out and make this 1 big room. I can't combine an S room on 1 floor with an S room on the next floor. It's like, well, we could get creative and build a staircase in between them. Yeah, not going to happen. Okay. Any other questions?
So what's the principal energy level for the or is there one?
Well, so the energy for this is between these, but it's still on the 2nd level.
Okay.
Yeah, it's still on that floor.
Okay.
It's just we've combined them into 1, and so there's a little bit different.
Okay.
Okay. So let's look at these orbitals and what shape these might have. So these are our standard orbitals. We've got the S orbital and the P orbitals that are kind of dumbbell shaped, and they're perpendicular to each other. So you kind of have to use your imagination here. But if we took these 4 shapes and averaged them together, we're going to get 4 shapes that are the same, and they're going to be spaced out equally. So we're going to end up with something that looks a little more like a turkey drumstick here. It's got a big lobe on one side and a small lobe on the other side. It's not symmetrical anymore. These are going to be the same in shape, but they're going to be spaced out. So four things, this is like the four balloons, this is going to take the shape of a tetrahedral because they're spaced out, they're trying to get space from each other. The big lobe here is the more important one, and this little puny one over here is not important. And so to make the drawings a little easier to look at, we usually don't include that part. So here we're taking the big lobes and putting them all together in one picture, and that's what we get. And notice that we had blue and red, and what happens when you mix blue and red? You get purple. So these are a combination of red and blue, right? They're a combination of S and P orbitals. These are the hybrid orbitals. Any questions?
The other ends, they're still there then?
They're still there, yeah.
Okay, it's not for the sake of the drawing, okay.
It just makes the drawing way too hard to look at, right? And remember, this p orbital is not a fixed container for the electron. This is like the standing wave that the electron is, because an electron is a particle and a wave at the same time. So this is like a standing wave, and so we're taking all these different waves and we're combining them together. It's hard to understand how you would do that mathematically, but somebody else did it. Yay for them. And we end up with this. So now we still have a standing wave, but it's not symmetrical. One end is small and one end is big. But because this end is larger, that gives us better overlap. This is the end that's going to overlap with another atom. And this little puny end, this little stubby piece is there, but that's not involved in the overlap. So if we make our sp3 hybrid orbitals, we moved our s room and our p room together because we took the wall out in between. Now we have 4 beds in the same room. When we put 4 electrons in there, 1, 2, 3, 4, they're each going to have their own bed, right? Because why pair up if there's no benefit to that? So now carbon has 4 half-filled orbitals. So when it interacts with hydrogen, hydrogen has its s orbital that's half-filled. So carbon hybrid orbitals, those are these purple ones here, and then this is the s orbital from a hydrogen. And so we get overlap, and you say, well, these both are spin up. Yeah, but they can switch, right? Just like you can choose to sleep right side up or upside down in a bed. So one of these is going to flip so that they're spin paired, and then they get along really well. So now this is predicting that carbon will bond with 4 hydrogens, and then it'll form a tetrahedron, which is what it does. We can have lone pairs in here as well. That's not a problem. So if we look at nitrogen, so nitrogen can form sp3 hybrid orbitals, and nitrogen has 5 valence electrons. So we're going to put these electrons in just like we did to the regular atomic orbitals. 1, 2, 3, 4, and the 5th one is going to have to share. So the 5th one's going to share. Well, that is a lone pair. So nitrogen has the hybridized orbitals here, making the shape of a tetrahedron. One of these orbitals has a lone pair, and the others are half-filled, and they're overlapping with a half-filled orbital from hydrogen. Okay? The bond angle here is 107, which is a little closer to an unhybridized orbital of 90, because when you have the lone pair in there, it affects the degree of the hybridization. So in Vesper theory, we talked about this taking up more space. I think that's a much easier way to think of it, and we can continue to think of it that way. Okay, So how many sp3 hybrid orbitals will you get when you hybridize one s orbital and 3 p orbitals? This is not a trick question. I got the two rooms, the S room with one bed and the P room with 3 beds, and when I make this into one room, how many beds are there? 4. Okay? If you have 4 orbitals and you hybridize them together, you get 4 new orbitals. Okay? Yeah, not a trick question. It's like, wait a minute, it couldn't be that easy. Well, yeah. It's almost like a trick question because we don't often ask you easy questions. Okay, well, what if you have 3 orbitals that hybridize with each other? So again, I'm going to draw the hotel floor here. So there's that S room. And here's the P room. So now, this group of electrons is coming in, and for whatever reason, they want a room with 3 beds, but they don't want to pay as much as just to go all up to the P room. And so the hotel's going to remodel the hotel for them. So I want 3 of these orbitals hybridized. You always have to start with the S, and then I'm going to take 2 more. So we moved the wall. We took the wall out between the S and the P room, and we built a new wall on the other side of those 2 P beds, so that this guy is off in his own room now. So this orbital has not changed. It's just an unhybridized P orbital. But these 3 have changed. And so we're going to call this sp2 instead of spp. So this is an sp2. Those are sp2 hybrid orbitals. So we took the S and 2 of the P, we hybridized those together, we get 3 degenerate orbitals. They have the same energy. And this guy is left unchanged. Okay? So this is what that would look like. The S orbital and 2 of the P orbitals. Again, we're going to get these kind of drumstick-shaped things, but now there's only 3 of them. How do 3 balloons arrange themselves when they're tied together? They make a triangle that's flat, right? So these 3, they're going to make a trigonal planar shape. So let's look at H2CO. This has sp2 hybrid orbitals. So we take the original S and P orbitals, we hybridize them, we move that wall over, and now what's going to happen is instead of this 4th electron pairing up in here, it's actually going to go up to the P room, and that's because the difference in cost, the difference in energy between these is a lot less now, and the benefit of having its own bed makes it worth it for that electron to go up there. So here we have our original orbitals. Here's hydrogen. Oxygen has 2 half-filled P orbitals. Here's our original carbon. But when we hybridize it, we're going to get something like this. And now the carbon can form 4 bonds. So here we have our sp2 hybrid orbitals. Those are 3 orbitals, like 3 balloons, flat triangle. Those are each half-filled. So one of those overlaps with hydrogens half-filled, another overlaps with another hydrogen half-filled, and this is overlapping with a p orbital on oxygen that's half-full. And what we've got left is the unhybridized p orbital from carbon and the other unhybridized p orbital from oxygen.
So the second bond would be right.
Yeah, it doesn't work.
Sorry.
No, I'm just like, I was trying to draw something, this is not going to work. So, this bond is, we got these like dumbbells or drumstick shapes, and they overlap end to end. That's called a sigma bond. And if you imagine standing here at oxygen's nucleus and looking towards carbon's nucleus, what you'd see is something that's round, right, and symmetrical, like the letter sigma, right? The letter sigma is like an O with a funny little tail at the top. When these p orbitals overlap, they kind of have to bend over and stretch to each other. It doesn't work as well. And these, I don't think they intended it this way, but that kind of looks like the letter pi, if you tip your head to the left. Yeah? So that's a pi bond. Pi bonds and sigma bonds. So the pi bond happens when we have parallel p orbitals that overlap. And so they kind of stretch towards each other to overlap at both sides. Now that looks like a double bond, doesn't it? It looks like two bonds, but it's only one bond. Because this is a standing wave, right? The electron is on both sides at the same time. And this is a standing wave. And so when these overlap, we have just a differently shaped standing wave. And so this pair of electrons is actually on both sides of the nuclei at the same time. Well, so we have electron density between, but then we have these nodes where the electron is never present. And so that's where, that wave-particle duality is like, electrons are really, really weird. They can be on one side and on the other without actually going through the space in between. Yeah, weird. So that's that pi bond. And again, it kind of looks like the letter pi. If we have orbitals, p orbitals that overlap end to end, this is called a sigma bond because it's symmetrical. It's a sphere if you look at it from the end. That's how I remember it. So this is that same picture. We can label these bonds to indicate what atoms are involved, what kinds of bonds they're forming, and what orbitals they are using. So this bond here is an end-to-end overlap, and so that's a sigma bond between carbon and oxygen. The carbon here is using an sp2 hybrid orbital. The oxygen is using a p orbital. This bond is also a sigma bond between carbon using an sp2 hybrid orbital and hydrogen using an s orbital. And so these two bonds have the same notation because they're the same kind of bond. And then this guy, which is the part on the top and the bottom, is one bond. That's a pi bond, and that's between a p orbital on carbon and a p orbital on oxygen. Pi bonds are always between unhybridized p orbitals. The hybrid orbitals are always going to make sigma bonds. So we get more insight into the molecule and the bond than we do with the Lewis model. The double bond between carbon and oxygen does actually have two different kinds of bonds. One is easier to break than the other. That's the pi bond, because the overlap just doesn't work as well. It's kind of strained. So whenever we're looking at a double bond in Lewis theory, that corresponds to one sigma and one pi bond in valence bond theory. The pi bond is easier to break than the sigma bond. If we have these two similar molecules, right? They're both carbon, hydrogen, and chlorine. But this one has a single bond between the carbons, and this one has a double bond between the carbons. This sigma bond is able to rotate. some very helpful person took it apart. I'm sure they thought they were doing me a favor, but now I have to make it all over again. So I'm making this model using the ball and stick model kit that we have here. I thought, oh great, I'll just use the one I was using yesterday. Not so much. I know this is kind of tedious for you guys. Not exactly parallel laughs for me. There we go. Okay, so here's the model of this molecule, and there's a single bond between the carbons, and just like, you know, if you put your fingers end to end, you can rotate one hand and still have them touching, right? So here, around this bond, there's rotation. And so we can have the chlorine atoms on opposite sides of the carbon-carbon bond or on the same side, and it actually just rotates freely like this, okay? When we have the double bond, though, that's like if you take two fingers from each end and touch them to each other, and now you cannot rotate one hand without breaking one of those bonds, right? If I want to rotate those, I'm going to have to break one of the bonds to rotate. So what happens with this model, when we have this double bond, we have little bendy pieces for this. When there's a double bond in there, you don't get any rotation. And that's a really important concept in OChem. So we don't get any rotation. Rotation is restricted. And valence bonding theory explains this, while the Lewis model does not. This is showing space-filling models of the same compounds.
They rotate?
Yeah, they rotate. With a single bond, it can rotate.
Huh.
Yeah. So here, we can have these two, this looks like two different molecules, but actually it's just a single molecule in different forms. It can just spin around. So sometimes they might be on opposite sides, sometimes they might be on the same side, but they can move.
Is it continuous rotation, or is it like they just kind of...
I don't actually know if it's continuous rotation. There are actually some things where, you look at these chlorines and they're kind of big and bulky, and they actually don't really care to be next to each other that much. So they're actually not going to be close together as much as they are going to be further away, but they can definitely twist around if needed.
Oh, they just twist?
Yeah, it's just the one spins relative to the other. When we have the double bond here, now we actually have two different forms of this molecule, and they cannot interconvert without breaking a bond. So here we have the chlorines on the same side, which is like the model I made, and I can't make it into the other one without breaking chemical bonds. I have to actually break the bonds to make it into the other one. And so those are two different forms of the compound, and they're going to have slightly different properties. Okay. I don't want to do that one either. Okay. Let's look at sp hybridization. So here we've got the s orbital, and we're just using one of the p orbitals. So then we have two unhybridized p orbitals that get left over, and these two now are between the original two in energy, and they're the same, and these are the sp hybrid orbitals. So when we look at these, we've got one S and one P, and when these combine, we get two drumsticks again, but they're opposite to each other. They're going to make a line in space. So again, looking at carbon, if we look at, this is acetylene. If we look at the carbon here, we see that it has how many electron groups? Not how many bonds, how many groups? A single bond is one group, a triple bond is one group. So this carbon has two groups, and that carbon has two groups. And that's what tells us how many orbitals we need to hybridize. We look at the number of electron groups. Ooh, that didn't work very well. I'm left-handed and I'm trying to write on my left fingers with my right hand. Went better yesterday. This is easier. So we look at the Lewis structure and we see how many electron groups do we have? 2. 1, 2. I need an sp hybrid orbitals. If I have 4 electron groups, 1, 2, 3, 4, I'm going to have sp3 hybridization. If I'm going to have 3 groups, spp. Okay? So when we hybridize it this way, again, these electrons are going to take their own beds. There is a little bit of extra cost here, but it gets offset later. So now we have, again, 4 half-filled orbitals. And now we can see carbon is always forming 4 bonds, isn't it? Because it has those 4 valence electrons. So the hybrid orbitals are going to do the sigma bond thing with one with hydrogen and one with the other carbon. And then we're going to have these 2 unhybridized p orbitals that are half filled that are just kind of left there. So here in the purple is the hybrid orbitals. This is one sp orbital overlapping with hydrogen and another sp orbital overlapping with an sp orbital from the other carbon. So those are forming sigma bonds, the end-to-end overlap. The hybrid orbitals are always going to form sigma bonds. And this carbon has 2 sp orbitals, so one of them's overlapping with carbon and one's overlapping with the other hydrogen. So here's the structure here. That middle bond we can think of as being this sigma bond here. But then we have 2 p orbitals, one in the vertical and one in and out, right, on each of these carbons that are half filled. And so the 2 that are vertical can overlap side to side and make a pi bond. And the ones that are horizontal coming in and out of the screen can overlap side to side and make another pi bond. So that is a triple bond, even though it might look like 5. But these pi bonds have a piece on both sides. So this is one pi bond here, and this is another pi bond there, and then we've got this purple sigma bond in the middle. Questions? What's the hybridization of carbon in CO2? We need to look at the Lewis structure. That's the Lewis structure for carbon. How many electron groups on carbon? 2. So what hybridization do I need? sp. So you can write on your fingers if you want. It wears off after a few days. Or you just say, well, 2 groups. I start with S, and then I only need 1 p orbital to make 2. If I needed 4, I'd need to take all 3 of the p orbitals. So this is going to be sp. Oops, that's not what I meant to do. So that's the hybridization. Well, we learned in the Lewis model that elements in period 3 and larger can expand their octets. And so in valence bond theory, this corresponds to hybridization involving the d orbitals. The energies of the 3d orbitals are similar to the 3s and the 3p. They're a little higher, but not a lot. So, on that third floor of the hotel, there's the S room and the P room, and there's also a D room. When we're looking at valence electrons, that D room's always going to be empty, but it's still there, right? Just because a hotel room doesn't have someone staying in it doesn't mean it disappears. It's still there, it's just empty. On the second floor, there's no D room. And so we can only get 4 hybrid orbitals together, and that will give us an octet. But here, we can take the beds from the P room and get rid of the wall between that and the S room, and then we can take one of the D orbitals. I haven't planned that very well. And bring that in as well. And then, so we've taken out 2 walls and we built a new wall here. So this is S, P, 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 and D, and so we call that SP3D. And the other 4 D orbitals just sit there. So here's the D orbitals, the P, and the S, and so we're going to take the S and 3 of the P's and 1 of the D's. You can't take an S and 1 or 2 of the P's and skip to the D, because that doesn't work in remodeling the hotel, right? You have to take them in order. So we end up here with 5 hybrid orbitals and 4 unhybridized that are left over. Well, we're going to make 5 kind of drumstick-looking hybrid orbitals, and they're a lot like the balloons. And how do 5 balloons get away from each other? They make this shape, right? Trigonal bipyramid. So here's the Lewis structure for arsenic pentafluoride. We look at this and we see it has 1, 2, 3, 4, 5 electron groups. 1, 2, 3, 4, 5 electron groups, sp3d. So, not sure why they changed the colors, but so instead of purple, it's brown now. But these are the 5 hybrid orbitals from the sp3d. Each of those has 1 electron in it. It's half filled, and so it can overlap with a half filled orbital from fluorine. And so we get this shape. We could also move the wall a little further and take 2 of the d orbitals. And so then we're going to call that sp3d2. That gives us 6 orbitals that are the same in energy and 3 leftover d orbitals. So now we've got 6 balloons, and 6 balloons are going to make this octahedral shape. So here an example is sulfur hexafluoride. We've got 6 fluorines. We look at the Lewis structure. The sulfur has 6 single bonds. 1, 2, 3, 4, 5, 6. So we need sp3d2 hybridization. Each of the hybrid orbitals will overlap with a half-filled orbital in one of the other atoms. Any questions? How do we know what hybridization scheme to use? Well, we're not going to do the crazy calculations where they're going to look at the degree of hybridization. Is it a full hybridization or is it a partial hybridization? What orbitals are involved? We'll let somebody else worry about that. We're going to go with good enough for Chem 3A. We're going to pick a hybridization scheme based on the geometry of the interior atoms, based on the number of electron groups on the central atom. Each electron group is one hybrid orbital. So this is kind of summarizing. These are the hybridization schemes. This is what they look like. And these correspond to these electron geometries from VSEPR theory. Again, you can get different molecular shapes because any of these hybrid orbitals could have a lone pair in it. And that's where we get the other shapes that don't have such fancy names. And we're going to save this for next time.